All right, so as you said, Tim O'Shea, I'm kind of dual-hatted DeepSig at Virginia Tech, and we're based in Arlington, which is right outside Washington, D.C. So super brief background. So I worked in SDR and AI applications, basically building modems for a while. I worked heavily on the Guinea Radio project, if you guys are familiar with that, which is an awesome enabler for building out software modems to test new algorithms and ideas. I finished up PhD in 2017. Got to do a DARPA study on some of the early work applying deep learning to RF back in 2015. And then DeepSig kind of came out of a lot of that work. So I licensed a lot of the IP and work I'd done at the university. And then DeepSig was founded in 2016. And now we're kind of a venture-backed startup, and we're really trying to be progressive in looking at what's useful in deep learning and comms and signal processing and building that out and building solutions that can go be used in the world and have impact. So I think it's a lot of fun because I love working on applied research and really transitioning things into real systems. And that's very timely. I mean, for me, machine learning for comms is very timely because I think that's a huge aspect of MLC is that vetting things against the real world is critical to testing and building out these sorts of systems. Right, so I'm excited to be part of WindMill, and I think it's a really cool program that you're all part of. So I guess it always makes a lot of sense to start asking yourself, does machine learning make sense for this problem? And I'm sure you've seen this before, and you'll see this again this week repeatedly. But again, it's like a super critical question to ask yourself about what you're doing. Does machine learning make sense? And there's kind of these two classes of model deficit and algorithm deficit, where model deficit is typically, all the system models for the problem are insufficient or don't represent the full distribution in the world, so we can do better optimizing for this problem. And then an algorithm deficit, really, you're looking at the solutions to this problem today, like iterative message passing and these sorts of problems are very high complexity. So can we find lower complexity solutions that save power, they do better? So really, you have to think about, don't just throw ML at everything. There has to be really a reason to want to do this. It only makes sense for some problems. And I think it's really important then to look at computer vision and voice recognition and other domains where ML has had a huge impact and ask, where has this had a huge impact? And so if you look at computer vision, obviously self-driving cars and object recognition are probably the biggest use of deep learning and machine learning that's out there today. And Tesla is one of the best examples of a really ML at scale, scaling up learning data from thousands and millions of cars and curating this all back to a learning process and pushing out new models. And so I think this falls into a couple core things that ML is really good at. And these are core problems that we have in comms too, but you have to think, does it fall into one of these categories, right? And so this is, do we have hard to model distributions? And obviously channel models and channel estimation and propagation and channel modeling come immediately to mind there. But there's other hard to model distributions in comm systems. But in other fields, voice modeling, natural language modeling, vision modeling, these are all things that are very, very hard to write a closed form model for that's accurate. Representation learning is another really, really exciting thing that deep learning has been able to do. So if we look at things like variational autoencoders and these kind of reduced dimension latent spaces that we can look at many, many data points in, this ability to learn new latent representations of very high dimensional data is fairly unprecedented in the scale at which we can now do it. And so being able to take difficult and high dimensional data and come up with effective latent representations of it, both for doing things like translation or sequence to sequence modeling, or compression has been another big application. as well as just sampling from distributions. And I think this is, again, when you think about channel modeling, being able to sample from distributions that are not of a very tight closed model is another really exciting possibility. So if you look at compute, it's hard to uncouple deep learning from the growth in compute capacity. And so this is actually a slide from Supercomputing 19, which is going on now. And this is really just plotting out, if you think about the size of the machine learning models over time, and you think about a single perceptron in 1960, and I believe the axis here is in like exaops to train a model. And so back in 1960, it took 10 to the minus 14th exaops to train that model. And we grew at kind of Moore's law, and now the claim is that we're doubling even faster because of the way microarchitecture is advancing right now. And so now we're able to train these enormous models like AlphaGo 0, due to the compute that's required. And so if you think about modeling a comm system or a signal processing problem, often the model complexity that we can deal with in an analytic representation is synonymous to a couple perceptrons. We have often a small compact formulation with like a weight vector, and so it's really important to keep in mind like the scale to which the models that we're training can now advance, right? We can go up 10 to the 20th times larger in the size of the parametric size and the operation size of these networks. And really the key reason for this is, again, this core change in microarchitecture. This is actually the Cerebus chip, but this is really the pattern that we're seeing between all of the different neural architectures, is that you're moving to memory cohabitated with the compute, right? So you don't have this bottleneck of I/O between memory and compute somewhere else. You have the memory pushed throughout the compute, and this is enormously more energy efficient and allows us to scale our models much bigger. And so this is really jointly enabling machine learning. We can't just think about machine learning without, in the context of the enabling microarchitectures. Right, so I then like to think about this in scale in the terms of the speed of iteration. And so, we've been going to more and more dynamic comm systems and radio systems. So, we started out with very static solutions. We moved to more software-centric solutions. And now there's this concept of software 2.0 that Andres Karpathy at Tesla coined, which is really this idea that software systems should be kind of learned end-to-end rather than programmed throughout a bunch of discrete modules with discrete logic, because you wind up with all of these unnecessary program space complexity. So you really want to boil your problem definition and your problem space complexity down to the minimum possible, and then allow it to optimize in a parametric space to come up with the right solution. And so I think we're seeing this in comms now. It's just that we're moving to more and more data-driven radio applications. And this is really exciting, I think, because it allows us to exploit a lot more information than we could before. And it shifts the role of the designer and the researcher and the engineer to like representing the problem. So making sure you can represent the right data, the right distributions, the right measurement tools, the right loss functions, and the right validation to really do this, right? And there's still absolutely work to be done in model improvements and in rigorous statistical validation of models. But there's also this an enormously more focused task on these sorts of roles, which were maybe not the focus when you were doing kind of smaller model validation in analytics sense. And so. Right, so so the speed of iteration idea that Boyd suggested, I think, is really key to this. It's that, even if we're not doing the best update, if we're constantly updating when these comm systems are deployed and making them work better in the real world, then we can often do much better than a solution that's not as flexible or doesn't iterate to match the world faster. And then Box, This is just the best representation of machine learning for comms that you could think of, because all these machine learning models have problems. We have trouble having rigorous probabilistic proofs and bounds for all of these things. These models are wrong too, but all of our analytic models were totally wrong to begin with. We had channel models that assumed, relatively simplistic models for very complex physical propagation phenomena. And so really, and I think this is to echo everything Peter said in the last talk, is that really we just have to be cognizant of how our models are wrong, what assumptions are wrong. Yeah. So I break this down into like two key functions, or two key tasks, and then there's many different versions of these in ML for comms. But in the physical layer, generally there's two things you want to do in the spectrum. You want to sense and be aware of everything that's out there, basically make sense out of what's going on in the spectrum, what emitters are out there, who's interoperating in each band. And then you want to be able to encode information over a wireless channel efficiently, just to maximize the multi-user capacity, the energy efficiency, whatever metric your network most needs for users or for cost or for difficult propagation. And so these are kind of the two core tasks that a lot of it breaks down into. So for understanding the spectrum, again, I like to look back at computer vision and say, well, what are they doing? What worked? And so looking at single shot detection is a great example. So the idea of single shot detection is that you train a network to take in an image with a bunch of pixels and then output a whole bunch of different regressions that tell you basically delta x, delta y of where a box is, width and height, and then pseudo probabilities for what that object is between a bunch of different classes. And so this is very much the structure that things like self-driving cars are using to do inference. And the thing that's exciting about this is that this is a constant time algorithm, right? It's just one pass through the network to get all the predictions of all the objects in a scene. And so this is very fast. We don't have iteration. We can parallelize it on these very distributed architectures. And so this is what makes it exciting. I think it's important to look at, well, you're not just throwing something into a neural network and doing binary cross entropy and everything magically gives you a confusion matrix. You can actually design much more complex loss functions. This is kind of the loss function that is used for I believe this is the YOLO, or you only look once loss function. And the idea here is that you have all these regression outputs and cross entropy outputs, and you can build these complex loss functions which incorporate all of these features and then just throw enormous amounts of data at it and actually be able to train a very large model to do all of these regressions and classifications jointly. And it's kind of incredible that this works, but this works really well. So we looked at adopting this or adapting this to wideband spectrum energy classification. And so really, if you look at the problem of many comm systems, it's what do I have to interoperate with when interference is in the band. You need this awareness that we don't have today. And so we kind of looked at adapting this using an approach that's not too dissimilar from a single shot detector to these sorts of problems. And what's exciting is, you can start to look at new metrics. So, traditionally a lot of comm systems have used, a CFAR kind of analysis, but, things like they're using in computer vision, like precision and recall, are actually really good metrics that we can also use in radio and comms here. Since then we've been really focused on building this out into production software. So I think most folks in machine learning will tell you that they spend like 90% of their time on data and data management and data curation. And that's a challenge for research in this field in general, because you don't really want to spend all of your time doing that. But at the same time, it's somewhat critical to do that, to have valid results and valid training. So I guess, open data sets are an amazing tool in that they can help people bypass a lot of the time and labor that goes into data collection, data management, data curation. But it's, if you're diving off in a totally new avenue with a totally new data set, you need to be cognizant that that could be an enormous amount of work to build your own data sets and do it properly. Right, so just to give you a sense of scale, when we train up these models, we're looking at data sets that are on the order of hundreds of gigabytes to train these things very, very well. And there's a lot of problems that will come up, right? So you have things like class imbalance, you have structured biases in your distribution, like what classes are relative to other classes in your data. These are all things that your model will overfit to if you're not cognizant of them. And so being cognizant of all of the biases in your data is super critical to be able to train these things effectively. And there's a lot of methodologies to overcome this, but you need to know, you need this intuition for what's going on so that you can compensate for it. And then this thing of continuous monitoring for anomalies and failures. We always overfit, and it's really hard to generalize to the whole world when you're building a machine learning based solution. And so if you look at Tesla again as a good example of this, if they have low likelihood events from all of the cars out there, they'll send data back that goes back up into the cloud, helps train new models, gets annotated, pulls in humans to curate it. And so there's this thing that, machine learning based algorithms take an enormous amount of hand-holding and maintenance and data growth and curation to really become production systems. And so it's hard, I think, to some degree, to draw a line between research and production in this field. But what's really exciting about this is that there's things that we can do that we could never do before. So if you look at like wireless activity monitoring, we could never really do this effectively at scale before, right? So operators today look at mostly network side KPPs to know when there's things going wrong or if there's problems with the network. But when we do things like this, you can now provide a much more comprehensive view into what's going on the radio interface. And so this is an example of looking at, the distribution of Wi-Fi and Bluetooth activity in a band over a week. We can start to see patterns of life and behavior when the spectrum's used by different applications and when it's not, when there's anomalous bursts that are kind of unknown. And we can start to do this analysis to really understand what is the distribution of the things going on in the spectrum, because we need to build our comm systems to actually match that and optimize for that. And then the other thing is this gives us an enormous power to then do other things like anomaly detection, change detection, alerting on device failures. And so there's all these things that we're not doing today, and in some of these cases there aren't good baselines. The rest of this, I want to talk a little bit more about. The other half of this is basically optimizing transmission of information in the spectrum. And so, this is the basic, simplest form of your autoencoder. It is just basically turning wireless comms into a representation learning problem. And so this is really kind of exciting because because of the power we've seen in representation learning in other domains, right? So in compression, in natural language translation, we've seen that this can learn very, very complex high-dimensional distributions and representations that transfer them effectively. And so here, we cast this as a joint learning problem between the encoder and the decoder. In a clean formulation, you've got perfectly represented channel that you can differentiate over. And it's really, I think, a new way of thinking about how to synthesize a comm system. And it's very kind of easily extended to multi-user, multi-antenna, and a lot of different applications. So there's this question then, is what do you do with it? And I think, we're kind of going down the two avenues, and I think there's two really valid avenues of research here, right? The one is kind of the green field, like I could throw out everything our comm systems do today and reimagine what is a modem, what does a modem look like, how does it encode information, and come up with entirely new representations there. And this is kind of the 6G thing of like, well, let's not worry about compatibility. Let's just try to build something amazing now that's learning based throughout the whole stack. And then there's the other approach, which is, well, do we focus instead on like just key problems and algorithms that are pain points in today's comm systems that are either driving cost or driving power consumption or degrading performance, and trying to really focus on specific algorithms where you're doing representation learning within a modem. And so those are kind of the two avenues to look at. And so there's tons of open problems. So this is just a couple of the open problems. I think if you look at this channel estimation problem of, well, I don't have a differentiable channel, I just want to learn this representation over the air based on measurement and sampling of a channel. There's a couple approach. There's the work that Jakob and all have done looking at a reinforcement learning approach to this. There's also methods like using GANs to come up with channel models to try to represent the distribution over the channel so that you can go back and use it as a differentiable model. So there's a lot of ways to do this, and I think that there's a lot of other ways that we haven't explored yet there as well. Scaling this to really effective large blocks for integration in comm systems. I think that there's really exciting work now in this kind of non-weighted source information where you're trying to do joint source and channel coding, and then really just exploiting more degrees of freedom. So going up and down the comm stack, there's work both going up into the MAC and now going down into the ADC to come with like nonlinear quantization schemes. And so, moving this out in multiple directions within the comm stack all has a lot of fruit. And then scaling this from a point-to-point system to a multi-point and a mesh and a distributed learning system is really not a solved problem. And so all of these are totally open. I think it's an exciting field of many, many, many problems right now. And so this is just showing kind of using an iterative scheme, converging a higher order channel autoencoder over the air here. But then there's a lot of other things. So if you want to actually scale this into a tool, like a software modem that can be deployed and used in production, there's all kinds of other considerations. Really trying to integrate with higher level error correction, with encryption, with video streaming and Ethernet and IP and MAC protocols that help enable this. And so there's a lot of other considerations there. And then just to show, some of the more standard-centric work we're looking at, this is an example of basically a fully learning-driven estimation and equalization process for 5G NR, where you can take a full L1 stack, the transmitter and the receiver, and then you can start replacing kind of selected components in the receiver with end-to-end learned solutions. And this is exciting because this is exactly the problem of like, I've got a very complex channel distribution in the real world, and how do I exploit that? Like, how do I take that distribution and come up with a better estimator, which is cognizant of the real distribution of the channel in the world? And so doing this, you have to come up with really good metrics. Like here we're looking at EVM and bit error rate, and we can compare kind of a 64 QAM performance to both approaches. And what's really exciting, I think, about machine learning is that you might have a 2 or 3 dB gap performance between MMSC and learned, but there's things like this. This is actually in the 900 megahertz band, and you have bursty interference, right? And so these are things that are not accounted for typically when we train equalizers for these sorts of things. And so if this is now in the data, and I can do online learning with this sort of behavior occurring, well, I can actually learn a lot better performance during this kind of bursty interference. Like these are bursting up to 5 or 6 or 7 dB of improved performance during these kind of interference events. So this is just an example of like there's all of this rich like information in the measurement in your deployed environment, and that's really the goal of capturing it in your ML comms system. So yeah, so there's lots and lots of pitfalls that you should think about. Does ML really make sense for the problem you're looking at? Can you get your hands on real data for this problem so that you can show it in the context of real data? Can you do it over the air? I mean, can you test it in an SDR and a test bed solution? And then can you come up with really robust metrics to compare it to baseline solutions? And so hopefully you can answer yes to all of these. And then it's a really good ML comms problem to focus on. And I think right now, if you look at the research landscape, there is, in some sense, a higher barrier to good work in ML and comms, because not only do you have to show that your method is better than the baseline, but you have to really show that your data and your test methodology is robust and it's sufficient to show it and it's believable. And there's so many ways to screw up your data, your biases, So doing something like going over the air is a really good way to ensure that you're not too overfit to one situation. So definitely, if it's possible for you or your problem, like it's always good to do this in the real world early. Change your environment wildly. So that you're sure you're not overfitting to certain conditions or situations, and your data sets, you really don't want to pick a problem where you can achieve 99% accuracy, right? You should have data sets that are hard, that you can hit 40%, right, or something low, right? You really make sure you choose robust data sets, and then just from a software engineering side. As I mentioned, IPython notebooks are really, really an awesome tool, but they're not a good software engineering building block. And so as you start working on teams and projects, be careful of like how crazy the massive IPython notebooks can grow as well. But there's a lot of exciting things. So getting real measurement data is easier than ever now with the software radio tools we have out there. You can go buy these RTL SDRs for like $20 and start doing data capture in real RF environments. You can get software radios like the USRP that help you get and transmit data very easily. And you can just go and use these. There's a lot of open source software out there that can get you going much faster in measurement and building this. So if you look at, GNU Radio, gives you a really nice tool to go out and do measurement, build on top of existing modems, so you don't need to implement all your baselines, and so that you can use code that's been vetted and that's trusted and is immediately a credible baseline for your work. And then there's also like this entire code archive, CGRAN, out there that has modems like 802.11 and Zigbee and GSM and Tetra and P25 and DAB and many more just already out there for you to use. And so if you need baselines to compare against and to test against and to help build up the software infrastructure you need to do machine learning on comms, these are really, really great resources to go and use as much of this as you can to build on. Yeah. So that's all I have. I think it's a very exciting time for ML comms. And we're definitely hoping to work with you guys more throughout this program as it goes forward. Hopefully be a resource for helping test things over the air in SDR type systems. Thanks.
Yes, we have time for maybe one or two questions. Comments? Yeah, I have a question actually. So you mentioned data curation, and it actually seems that it's becoming increasingly important. So maybe can you share some experiences you had with this issue?
Yeah, I mean, I guess it's interesting because if you look at computer vision, there's a totally different model. In computer vision, you've got Google and Facebook and these guys that have many terabytes of imagery out there for them that is their kind of monopoly and their private data set, right? And so they're very open with everything else. And I think the amount of time that they spend, if you go look at Facebook and all these programs, they'll have a specific team focused to data labeling. They may employ a 20-person or 100-person department just to label data because it's that laborious. And I think it's a hard task. I mean, we're lucky, I think, in comms that many of the things we want to label we know about. Like if we're transmitting a test signal, we know we can log when it was transmitted. We have a lot of non-machine learning based signal processing to do detection and labeling to bootstrap. And so I think, for supervised learning, you absolutely need that. And there's a lot of effort to take the best of both worlds to try to, semi-automate that process. On the comms side, data labeling is amazing because, it's typically bits or code words. Like we're already doing this. We have checksums to verify them. We have, we know what we're transmitting for test signals. And so if you look at comm systems as a supervised learning problem, it's really nice for us that we don't need to worry about labeling lots of hard to curate things. I don't know if that answers your question. Yep.
So machine learning algorithms have been long time used for example, for analysis of network traffic in internet and so on. So it was one of the big applications of big data where these algorithms have been applied. And then if I compare the way, the easiness by which you can verify and generate data here is much easier than compared to, for example, pictures that people are collecting and so on. So do you think that the fact that our community has access to more data here can make some advancement in the machine learning area because we're in a better position to generate this data compared to others?
Absolutely. I think if you look at the problems I've focused on, it's been largely driven by the things I have access to data for. And I think a program like this where we have real industry involvement, access to real equipment, hardware, hopefully a real carrier, data traces. These are absolutely problems that you can't solve without the data. So if we can get access through the consortium to actual traffic traces that are representative of real world problems and real world loading, that's an enormous opportunity that I don't think anyone else can do. So that's a very unique advantage.